Hi again. This is another in our series of problem-solving videos where I try and walk you through the steps of solving the problems typical of the homeworks, of course also then of the midterms and exams, and to really help you lay out a strategy for solving these problems using what we consider good practices. So these are steps, not a recipe, but certainly steps that you can apply consistently throughout these questions. Now I thought I'd start with a simple example in this case. This is one straight out of the textbook, and the textbook also goes through the steps, but I'll try and consolidate those steps and show you in a little more realistic setting how we'd go about solving this particular problem. So you can see now the circuit that we're going to solve, and now we'll jump over to the computer and we'll start there showing you how I go about solving this, just as you would in your, like I say, in your homework assignments and in your practice, and doing these problems again and again. All the examples you'll get, all the examples you'll see is the best practice that you can have. And as I walk through this, I'll try and point out some of the strategies, again, that you can use consistently throughout. So the first step in solving one of these problems is always to draw the diagram. You can see here I have a diagram all drawn out, hand drawn out here, with a little help from my clever drawing tools, and you can see that I've labeled everything. That's another hot tip. Don't put numbers into a problem. Use variables. It's a really simple rule. Apply it, and I promise you, you will have better success than if you start sticking numbers in too early. So this problem is laid out with the variables already named for you, but you can decide for yourself in other cases what you want to call the resistors and the voltage sources and the currents even that flow here. But we were given this problem, and we were asked to figure out the current that would flow through the R3. That's what we're going to solve for, is R3. That's the current that flows through R3, and we'll eventually get down to that point of figuring out what all this leads to. And like I say, we'll go through all the steps and show you what the ultimate answer is. And you should be warned that this is not so straightforward. The algebra here will end up being one of your biggest challenges, because you'll have to solve not complex equations in here, sets of two equations, two linear equations, but there'll be a lot of variables to keep track of. And so writing clearly, being consistent on your variables, checking at every line you write are all key tips to help you improve your success. So let's get started. So what we have here is the diagram of the circuit, and we can solve this lots of different ways, and I'm going to set out to solve this for you using, like I say, the standard set of steps. And so I'm going to switch to blue here, just so you see that the blue will be the steps I'll carry out. We'll switch colors occasionally just to help us. And so the first thing, once we've got the diagram figured out, is to label the currents and then the resulting voltage polarities. Really, we don't know the voltages yet, but we know which is going to be plus and which is going to be minus. So, and it's traditional to, for example, take the resistance, or yes, to take the resistance R1 and say the current that is going to flow through that, I'm going to call I1. And the minute I draw I1 in that direction, then I am forced to put plus and minus in those polarities. This is the convention that we have to adopt if we're going to use this Kirchhoff-Tuer method. It's robust, it works very well. So we have another current down here, it's called I3, and of course that dictates that we have plus and minus labeled like this. And you remember that we had incoming currents and outgoing currents, so let's call I2, which we'll draw up here, an incoming current, and we'll label it and point it that way, and that means that we'll have a plus here and a minus here on the resistors. And with that, we have a pretty completely labeled diagram. Now we're going to have a couple of nodes to deal with. We can pick either node because they turn out to be equivalent. They'll give us the same equation, and we can start imagining already that these currents are going to sum to zero because of conservation, and so we're going to need one of those nodes. And again, you can pick either one that you want to write an equation for. And we will see that with three currents like this, we'll need to write down two separate equations for Kirchhoff-Tuers as well as the equation for the currents in order to solve this problem with these three variables, because we're going to eventually have three equations for three variables, the variables being I1, I2, and I3. The one we're interested in is I3, and we'll finesse that so that we get a good answer for I3. Now, the next thing we have to choose now, there's no fixed rules here, is what sort of Kirchhoff's tours that we'll actually carry out. I like clockwise tours. I don't know, you may like counterclockwise tours. You can try both ways, and in fact this is a good way to solve this problem multiple times. So I'm going to take a Kirchhoff's tour here. I'm going to call it KT1 just to keep it straight in my head, and then I'll have another tour here and I'll call it KT2. And again, this is just for labeling's sake. So now down below I can start to write out things like the tour KT1 and what I find when I do that tour. Now the convention is that when we go in this direction, and again you can start anywhere. I'll start in, I don't know, the lower left corner. So if I start in the lower left corner, make my way around that tour, then I will see that I have a minus VA. Why minus? Well, minus is the first sign I encounter, and VA is the voltage drop across that voltage supply. If I go to the next element, I see that I'm going to have a voltage drop here that's going to be I1 times R1, and it's going to be positive because the first sign I encounter is a positive sign. So I have I1 R1 and that part of the tour. And then if I continue the tour, I drop down here into this middle branch and I see that I have also a positive sign, and then it's I3 times R3, and the sum of all those voltages is going to be 0. So that's the energy conservation Kirchhoff rule, Kirchhoff's tour law that I'm applying here. I can do the same thing now for the second tour, which again I'll start from the lower left corner just because that seems reasonable, and I'll say the current I3 is going through R3, but I'm encountering a negative sign, so I say minus I3 R3, and then I go across the top there, and once again I've got a minus sign, I2 minus I2 times R2, and then if I follow down to the right side I get another minus sign, VB, and that is equal to 0. That's the complete tour. Now I said I had a node to think about, so I have another node equation. So again, it doesn't really matter which way I look at it. If I take the top node, for example, then I'm going to see that the incoming nodes, I1 plus I2, are going to be equal to the outgoing node, which is I3. And I'll use that equation. And so with that, I really have all the physics, the analysis of the circuit done. From here on, it's really just solving equations. And that's something we need to practice. It will take time for many of you, and as it does for me usually. And so we'll just walk through this and see what we get. So now we can start to solve these equations. And strategically, I like to lay them out like this with KT1 on the right side, KT2 on the left side, because my usual strategy is to maneuver both these equations to the point where I can set them equal to each other, which means I have to have them set up in terms of one or the other of the currents. And I can pick either one. I can substitute the current relationship as I like it into one of the equations and then eventually solve for I3. So I'm going to substitute in on the left hand side, for example. I can see that I have an I1, and the right hand side I have an I2. It really doesn't matter which one you substitute for. But let's say I'm going to substitute for that one on the left, and if I look at this equation here and think how it's going to fit in this setting, then I can realize that I1 is going to be equal to I3 minus I2. And I can substitute that into the equation and write minus VA equals, or sorry, plus I2 now is substituted, I1 sorry, is substituted in to be I3 minus I2 times the R1 plus I3 R3 equals 0. Now again, my strategy here is to get I2 on the left hand side on both these equations. And I can continue with this equation, or I can move to the other equation, doesn't really matter. But the nice thing is that already I have both these equations, the KT1 equation, the KT2 equation, now in terms of just two variables. I have two equations, two variables. I know I can solve this. That's just what the math tells me. Practically, as I say, I want to get I2 in the left of both of these two equations. So if I move the I2 term, this term here, if I move that over to the right hand side and then sort of swap sides to make it easier, and again, you can do as many steps as you need to reduce the chances of you making an error, but if if I2 moves over to the right hand side and then I swap the whole thing over, then I can say I2 times R1, that's the term I just got from above there, is going to be equal to, and now all these other terms have stayed on this side essentially, and so here I'm going to have the minus VA, and I'm going to have a plus I3, and it's going to be multiplied by the R1 term that I already have there plus the R3 term. So make sure that step is clear. It's a good time to think again about what's going on, what we're really seeing here, and to make sure that we haven't made a sign. This is the classic location where we make errors in signs. So again, I2 R1, that moved over to the right hand side. Everything else here that was on the left hand side stays together with the same signs, and then I just flip the whole thing left to right. That's all legal algebra. And again, please do as many steps as you need to get this clear in your own head. But now I can write I2 equals minus VA plus I3 times R1 plus R3, and then of course divided by that R1 term. Now I can swap to the right hand equation, the KT2 equation, again with the strategy that I want I2 to be isolated, so I can set these equations to be equal. So now I can write the I2 R2 term, so that's sort of moved over to the right hand side, or the equivalent of that, and that's going to be equal to whatever is left over here on the left hand side, and that will be minus VB minus I3 R3. So now I have these two equations, left and right hand side equations, all set to set equal to each other. So these two equations are now going to be considered equivalent. So now I can write, let me scroll up here a little bit, so now I can write an equation that couples those two equations. So now I can say that I have a minus VA plus I3 times R1 plus R3 over R1 is going to be equal to, and now I actually took a shortcut here, sorry, I should have written this out. If I write I2, then it's actually minus VB minus I3 R3 over here divided by R2. So now I can set them truly equal, and I can say minus VB minus I3 R3 over R2. Okay. Now I have to work with these two equations. Let's scroll up, make a little more space. So now if I look at this, I realize I need to have them over the same denominator in order to solve this combined system. And eventually I want to have I3 on the left and the other terms left on the right. So I'm going to cross multiply. So I'm going to get a common denominator, which is R1, R2. Let's write it out in full and see what it looks like. So I'm going to multiply the left side equation by R2 over R2. And so that will give me minus VA times R2 plus I3 times R1 plus R3 times R2, and that new denominator I have is R1 R2, and that's going to be equal to, now the right hand side I'm going to multiply by R1 over R1, which is the same as multiplying by 1, and I'm going to say minus VB R1 minus I3 R1 R3 over R1, R2. So it's a simple algebraic step. Now, of course, I have the same denominator, so I can set the numerators equal to each other and start to look for sort of ways to clean this up. So I can write now out here the I3 from this first equation is R1 plus R3 times R2. I have that term. Now I have a minus I3 over here on the right hand side, which I can also move over here to the left, and I can say, well, I3 is equal to this left hand term plus my R1 times R3, and now I have that whole term. And I can always take a break and take a breath, have a drink, and think about this and look at this and do a unit check. Always useful to do unit checks. So here I have a current times the sum of two resistances, which is a resistance, times another resistance, so I have resistance squared, plus another resistance squared. So that all at least is sort of inwardly consistent. And then over on the right hand side, now I'm going to move these other non-I3 terms over. So I have VA times R2, so minus VA times R2, which is going to become, a plus when I move it over to the right hand side. And what do I have left from here that's not I3? Well, I have a minus VB times R1. And those are the terms I have left. Now again, unit check. On the left hand side we had a current times a resistance squared, and we know current times resistance by Ohm's law is equal to voltage. So the I plus times the R, one of those makes a voltage times R, and on the right hand side I have a voltage times R. So my units are good, and it's always useful to check on these things on a regular basis. The other thing, of course, to check on is to look at signs, make sure the signs are okay. Now I have a way toward a solution. So now I can say that my solution is VA times R2 minus VB times R1, and then down the bottom here I can multiply this out, and I see that I have R1 times R2 plus R2 times R3 plus R1 times R3. And with that, I actually have the solution for I3 worked out. And this is a perfectly reasonable way to leave it. This is a perfectly viable solution. Now we can find other ways to simplify this. We can rewrite this, of course, in algebraic terms, but this is a useful way to have the equation. Now what you'll notice in the textbook actually is we have a very different form for the equation. You might look at that equation 9.15 and you see that it looks quite a bit different. And we can show that we can actually get to that same point. To me, that's a messier form. There's a certain amount of redundancy, and I don't think we've really gained a lot by using that form. But we can certainly convert it into that form. And I would encourage you to either take 915 and convert it into this by making R1 times R2 the common denominator, just as we did effectively here, or take this equation and divide it accordingly to get those ratios you see. But you see the basic form is the same. We have a VA term minus a VB term, and then a bunch of resistors on the bottom. Again, the unit check is important. So up here we have volts times ohms for both those terms, and on the bottom we have ohms squared. And so what we're left with is volts over ohms, and volts over ohms is equal to amperes. It's equal to the unit of current, and sure enough we have I3 as a current. Now it's important to note that there are other ways to do this problem. There are other decisions you could have made. You could, and let's go back to the diagram that we had in the beginning here, you could now instead take those Kirchhoff's tools in another direction. You could, for example, take the Kirchhoff's tools in a counterclockwise direction. That's perfectly legal, and you could write the equations in terms of a counterclockwise tour. You could also pick the currents to have different directions. Each one of these currents is somewhat of a choice for you to make as to which way you draw it. And the key thing to remember is once you pick a current direction, you must then take that into account properly at the resistors that current flows through. So where I had, let's look back at our blue example here, where I had I1 defined this way, that meant that the current flowed from left to right through this R1, and that meant that this had to be a plus sign over here and this had to be a negative sign over here. That's the connection. So if you are consistent about that, you can now solve this problem with these other starting points, pointing I1 a different direction. You can point each one of these currents individually in a different direction and solve the problem again, and you can solve it again by changing the orientation of the Kirchhoff's tools. So there are many ways to solve these questions, and that's the best form of practice that I can recommend, that you just keep taking different starting assumptions, solving the problem, and assuring yourself that indeed you will get the correct answer, because at the end of the day, that's all that ultimately matters. So that's all we need to actually solve the problem. But there's another strategy that you need to learn that I want to explain to you today, and that's called range checking. So range checking has a very useful purpose. You'll see us ask for it. The homework assignment this week already asked for it. So what in the world is range checking? So range checking means that we make some variable in our circuit go to 0, go to infinity, something that will ultimately simplify our circuit and allow us to solve a simpler circuit where we're maybe less likely to make a mistake, and then compare the results to what we get by simplifying the solution, the actual algebraic solution that we got from the first part. So let's see what that means. All right, so let's start with the diagram we had before. We had the various currents and signs on it. Let me finish up with those signs. So now we have the plus and minus signs all laid out. So that's the circuit we started with. Now the idea here is to simplify the circuit, and we're always trying to get rid of a branch. Ultimately, this is sort of the goal that we set ourselves. And obviously, getting rid of the branch that includes I3, which was our solution, is maybe not such a smart idea. But we could get rid of this whole branch on the right-hand side if we set the value for R2 to be very large. Because if that becomes large as in toward infinite, then that whole branch goes away. So now I can literally erase that entire branch and simplify my circuit quite dramatically. I can get back to a really simple little circuit here in which there is no I2 current. There are only currents there. So we have a current I1 and I3, and I1 is actually equal to I3. There's only really one current. So now we can even adjust this and say this is I3 flowing here, but we have to have agreement in direction, and we do. I3 flowing as it does from left to right up here would flow down through that circuit. So now we can write a Kirchhoff's tuor for this equation. So we have just a single Kirchhoff's tuor to write down here, and we can write it going clockwise from the lower left corner again. We can say minus VA, because we're counting that negative sign first, plus I3 times R1, and then we go down here and we see plus I3 times R3. Sorry, that was meant to be a 3 here. Got a little bit mottled. Okay, so that's the equation we have. Now we can solve that in terms of, and sorry, that's equal to 0. That's sum. Now I3 is simply equal to the VA over here divided by R1 plus R3. Now that's a straightforward solution. It won't take you long to be able to write a single Kirchhoff's tuor and be comfortable writing those kind of solutions. But now what we need is the original equation we started with algebraically, and now we're going to simplify it by setting R2 to be a very large value. Okay, so here we have the solution that we just figured out, and I'm going to claim, scroll up here a little bit, I'm going to claim that we're going to make R2 get to be a very large value. So we're going to set R2 going toward infinity. That's our assumption here. Now, if we look at this equation, we can rewrite this equation, I3 equals, now R2 times something minus VB times R1. It's obvious what term is going to dominate this. It's going to be the VA R2 term. No matter what, as R2 gets bigger and bigger, that term will dominate. If we look in the denominator, then we see we're going to have an R2 term, which will be the big one again, and it's going to be multiplied by R1 plus R3, and that third term, the R1 R3 term, that's going to disappear in comparison. Now we have an R2 over R2 situation, so they actually cancel, and we have a very simple solution of VA over R1 plus R3. And if we scroll back here, we see that indeed that was exactly the same solution that we got when we used the simplified circuit. So that's range checking, when the algebraic solution that we get by substituting in an assumption about a resistance, let's say, matches the solution that we got by simplifying the circuit. That's range checking. Get comfortable with it. We're going to make you do it, but what's way more important than that is this is a great way to check your accuracy, because range checks are simple. They're always leading to simpler circuits where your chances of mistake are simply lower. And so you're more likely to be able to write down a one-line solution, as we did in this case here, where I was able to write a single equation for a Kirchhoff's tour, solve that, and come to this equation. And then I was able to compare it quite simply to the algebraic approach, where I started with my original solution, inserted the assumption that RT gets very big, and then was able to derive a very simple equation that said the same thing as the circuit. So when these circuit checks or range checks don't show up to be equal, then there's a really good chance that you've made a mistake in your original solution. And that can be a very valuable warning to go back and check it again, to run it again. So before you look at the answer in the homework problems, try and do a range check or two. In the homework this week, you'll have two at least to do on the same problem. So get used to doing these. Figure out a good strategy for them. They don't take a lot of time, and they can really improve the chances of you getting an accurate solution. So with that, I've given you a pretty representative example of the kind of problems we're going to be solving. This one had let's say a moderate level of algebra, a moderate number of variables, but the strategy of solving the simultaneous equations using the three equations you have is one you can replicate through many, if not all, of the problems that we have. It's a very typical scenario for these problems. There are other ways to solve linear systems of equations. Three equations, three unknowns. It's a classic scenario. There are other approaches. If you're more comfortable with one, if there's one you've practiced a lot and feel like it always works for you, another substitution type approach or an elimination type approach, then of course you can use those, but make sure to include the steps. When we look at your answer, we need to see the steps so that we can be convinced that you've actually done something in a reasonably logical way. I don't require you to lay it out as we did here with the two Kirchhoff's tours left and right on the page. I do think it's a very effective strategy, but it's not a requirement. Give it a try, see if it works for you. If you have another strategy, like I say, feel free to use that. I would say if you have a strategy that works consistently, stick with it. It's going to reduce the chances of you making an error. So solving each problem using a different strategy for solving these equations is really not a smart approach. Pick one, get to be good at it, get to be practiced with it, and it will hold you in good stead, and you'll do very well on the homeworks and on the exams that come up. Of course, if you have questions, let me know. Thanks very much for listening, and I hope this will be helpful for you.